Hello, I'm Professor Alex Pinto, and this is the video about determination of lattice parameters of a body-centered cubic metal using simulated X-ray diffraction data. In this video, we are going to calculate the lattice parameter of a metal with body-centered cubic unit cell. So we will be using two softwares to accomplish this task. First, we are going to use Vesta to simulate the powder X-ray diffraction pattern from the CIF file, and then we're going to use Excel. Okay, so the goal to calculate the lattice parameter, we need to program this equation, okay, on Excel. Which are the things we see on this equation over here? So we have the lattice parameter. It could be in nanometer or angstrom. That's all that's going to depend from how we plug the wavelength. So let's see each one of parameters. A is the lattice parameter, okay? Lambda is the wavelength of the incoming X-ray source. In this case, let's use the wavelength for the copper K alpha 1, which is equal to 1.54059 angstroms, okay? Then we see in the denominator 2 times sine theta. This sine theta is the sine of the half of the diffraction angle where the peak is observed in the simulated X-ray diffraction pattern. One detail here is that the peak, as it's presented in the X-ray diffraction pattern, the position is given in degrees. So before being able to plug a number on this equation, we have to take that number, convert to radians, and then divide by 2, and finally find the sine of that angle theta that's in radians, okay? Finally, we have the Miller indices H, K, L for each peak we see in the simulated powder X-ray diffraction pattern. So again, the goal is to finally being able to program this equation on Excel, and for each peak obtain a lattice parameter value, okay? Then we can average that value and find the average value for the lattice parameter for that metal. So that is the goal. Now let's start literally doing the task. First, we're going to start with the Vesta, and then after simulating the data in Vesta, we can go on Excel. So as I just told, we're going to need two pieces of software to be able to accomplish this task. The first software is the software Vesta, which can simulate the XRD pattern from CIF files that are downloadable from the Crystallography Open Database. To simulate the powder X-ray diffraction pattern on Vesta, first you open Vesta, then you click File, then Open, and then you select the CIF file that you're going to simulate. In this case, we're going to simulate a CIF file from lithium. We open that on Vesta, and as you can see, so you can rotate around any axis, and you see that it's truly a body-centered cubic unit cell, where we have lattice positions in the corners and one in the very center of the unit cell. Okay, so as the data is imported on Vesta, now we can simulate the powder X-ray diffraction pattern for that. So for doing that, we come here in Utilities, Powder Diffraction Pattern, which is the 6th option from top to bottom. And then you're gonna see a windows like this, okay, with 3 tabs: Conditions, Reflections, and Plot. So you come in the tab called Conditions, okay. This wavelength, it's like the incoming wavelength, okay, for the from simulate the incoming wavelength of the X-rays from the diffractometer, okay. To make things simple, these cases are the wavelengths for the copper K alpha 1 and K alpha 2. Just to make simple, let's give like just one wavelength, so like an average value for the copper K alpha, or simply the copper K alpha 1 for this case, okay? Then you'll see that reflections tab do not show anything, and the plot tab does not show anything as well. So you come here in the very left side and click calculate, and then you see that the powder X-ray diffraction pattern is simulated already, okay? So that's the information we need from Vesta to export from Vesta in order to keep our calculation or to start our calculation on Excel. If you click here in the tab Reflections, you see that there is a table that lists all the reflections, okay? So the HKL Miller indices, the D spacing, the scale factor, the two theta position, the relative intensity, multiplicity, and so on, okay? So we are gonna need only 3 columns from this file, okay? So we're gonna need the 8KL Miller indices and the 2 theta position, okay? One of the easiest way to work with this file, one alternative, I think the most simple one, would be like manually copy the data from Excel, okay? But like it's very likely to have mistakes on that case. So what I would recommend you is to first export this table, okay? So you've come here on this same window and click File, Export Reflection Table, which is the third option from top to bottom, okay? And then you save that here, okay? So my trial 4, and then that's going to save as a text file, okay? So you come to the folder where you saved that, so you open the file, okay? As we will need to export to Excel only four columns from here, so each one of 8KL indices and the 2 theta, one thing that you can do to easier process this is to delete any column we don't need, okay? So like this. And you do that for all the rows in the table. You see that the things are going to get like properly aligned all again, okay? Keep deleting the columns you don't need. And then you save this new file, so you see that now it contains only the 4 columns we need. So you see that it will be much easier to import the data on Excel. So after having prepared this input table, so let's go to the Excel, okay? We could, for this calculation, I would say beforehand that you could use like if you are familiar with any program language, that you could use that as well, but like to make things simpler, let's do that on Excel, okay? That would make things much more accessible for those students that are not familiar with programming, okay, or to any language. So to import data on Excel, each Excel version is very particular about the steps. This one that I'm using is the Excel from Office 2016. On that version, to import the data, you click here in the main menu in the option Data, And then on the top left, you have an option, get data, then from text/CSV. That's the one we're gonna use. So come here, and then we select the data that you want, import that, and you see that now it contains only the columns we want, okay, properly imported, okay, loaded, it's getting the data, okay. Just to make things simpler, let's format in a simpler way all the layout, so basically without any formatting, okay. And like to get rid of these drop down menus, I'm gonna copy to a new sheet, okay. So age, key, L, this color gonna call to data red. I'm gonna increase the zoom so you can see it better in the video. Okay, so this is the pick list that you want, that you obtained from Vesta by importing the data from the simulated powder X-ray diffraction of the lithium, okay? Just to keep the counting, so we have like in the column A, we have a column that will be like a counter, so like you're gonna count like peak number. You're gonna count how many peaks we have there, like 1, 2, 3, 4, 5, 6, 7, 8. So those are the 8 peaks we have available for lithium. Okay, so let's start the process. So actually this is in degree, these two data, sorry, so degree, okay. So you have the two data in degree here, and you have their respective two data. So the first step is to take these two data position and convert them from degree to radians. So let's see the function on Excel that is able to do that. So come here, insert formula, insert function, then there's a function called radians, R-A-D-I-A-N-S, radians. This function converts an angle from degrees to radians, which is exactly what we need at this moment. So select that. Select the position of the entry where the angles is in degrees, and then click OK. Okay, so that's what has been done for this first peak. So it told us that a peak that is equal to 36.17 degrees corresponds to something around 0.63 radians. Okay, so you can like put the things down on here on Excel, and then do the same operation for all the remaining 7 peaks, okay? So we have the peak in radians here. The next step is, let's take this peak that is in 2 data and divide that by 2, okay? So we're gonna have data in reds, okay? That's a relatively straightforward process to do in Excel. So we type the equal sign, then we click in the entry that we want to get the data from, and then complete the operation by dividing that entry by 2. Okay, so that's the case. So we see that a 2 data around 0.63 corresponds to a data around 0.315. Okay, and then we raster down the cursor to complete the remaining 7 entries. Okay. Next, let's calculate the sine of the angle represent the theta angle, okay, which in our case in this column G. Sine theta. The function Excel that does that is the function sine, okay, S-I-N, so returns the sine of an angle. Okay, so we have the sign of the theta angle on this case. Then the next column we have to square the sign. Okay, sine square theta. Okay, not a very difficult process to do in Excel. Just type the equal sign, click the entry, and then click the asterisk, it's the multiplier, and click again the same entry. So we are squaring the data. This is sine square of the theta. Next, let's look at here, okay, on all those values over here. And then what you're gonna do is we're gonna figure out which one is the minimum value, okay, the smallest value, which the case is the one for the peak number 1, okay, so this equal to 0.09636118. So we're gonna take all the entries and divide by this specific value, okay, so sine theta squared divided by sine square minimum. Take this one, divided by that, and then to lock this value in before you raster the cursor down, we have to put like a $sign before the letter and before the number, okay? So this entry is locked. And then you raster the things all down. You see that you see many significant figures on this case. On this case, let's make sure you have just one significant figure, okay, for this column. So we can reduce the number of significant figures on Excel. Okay? Next, we're gonna take the result from the previous column, from this column J, and multiply that by 2, okay? Why by 2 on this case? It is multiplied by 2 because each unit's body center cubic unit cell contains 2 lattice positions, two complete atoms contained within the unit cell, okay? Because we have 8 corners, okay? Each corner occupies 1/8, okay? So we have one complete lattice position that comprehends all the lattice position in the corners, and then one lattice position fully inserted for the lattice position that's in the very center of the unit cell. So we have 2 lattice positions fully inserted within the unit cell. So I take the results on the column J and multiply that by 2. Times 2. Okay, let's leave just like all the numbers before the decimal point. Then you're going to come back to the second, third, and fourth columns where the Miller indices are contained. Okay, so those are the Miller indices. Okay, so what we're gonna do next, we're gonna take these Miller indices, okay, and we're going to square them. Okay, so we're going to square H square, K square, L square, and do the summation of them. Let's go here. We can do straight here, sorry. So we can do H square plus K square plus L square. Okay. So the equation is we take this and multiply this. this. Then we're doing the K square right now. And then let's do the L square. And then you can raster the cursor down. Okay, so look at the values on the column key, which like the sine square divided by the minimum, the square sign of the minimum value multiplied by 2, okay? And then we'll see that the H square, Q square, L square, so the values agree completely, okay? So if the values agree in these two columns, they completely agree, it's an indication that all the calculation we've done up to this point has been done completely correctly, okay? Then the next thing to be done, we are gonna enter the Lattice parameter equation, okay? So which you can see in the screen right now. The next step is to take the square root of the values we found on the column L, okay? So we're gonna copy these. Square root, for that we use the function. Let's look at that. SQRT, okay, that's the function for square root. Okay, let's have more significant figures here. Okay, so that's the square root. Now that you have the square root, for that, we can calculate the Lattice parameter equation, okay? So take the lambda, the wavelength of the incoming X-rays, multiply that by the square root of the H square plus Q square plus L square, and divide that by 2 times the sine theta, okay? Which is in the column J, which is in the column H. So let's do that. It's equal to, let's come back to Vesta to see what is the lambda. So 154,059. Okay. Then we multiply that in column M. Then divided that by 2 times sine theta, which is in the column H. So this is the Lattice parameter in angstroms, okay? Angstroms. This is the Lattice parameter for the peak number 1. So you can raster the cursor down. Okay, and then we can take the average. So average A and the standard deviation for A. Formula, insert function, average. Average all these values here. So 3.50929, and then we have the standard deviation for that as well that you can calculate from Excel. Insert the function stdev.p. okay? So pretty small, so in the order of magnitude of 10 to the minus 8. So this is the average lattice parameter we calculated using the steps described in our course, okay, for this experiment, okay, describing this. So you can do this, follow this same template, this same order of columns, all those steps for any body-centered cubic metal, okay? You can simulate on Vesta, get the CIF file from the Crystallography Open Database, simulate that on Vesta, pretty much the way we saw in the beginning, and then you can calculate the lattice parameter following on Excel, following these step-by-step instructions we saw on this video, okay? I hope you have enjoyed and learned something useful from this. Thank you so much for watching.